A warm welcome to the 6th session in the 4th module of Signals and Systems. We are now getting familiar with the Laplace transform and the Z transform. We now need to put down certain properties. We could keep taking examples, but it will be easier for us to write down certain properties, to investigate certain properties that these transforms obey, thereby leading us to deal with a much wider class of signals, both continuous and discrete independent variable. So, let us begin with the first very important property of linearity. Now, when we say linearity, what we really mean is, think of the Laplace transformer or the Z transformer as an operator. So, you are saying you have this machine called a Laplace transformer. It takes the signal x t and generates capital X of S with a region of convergence. And let us write region of convergence to be script r capital X. So, this means the region of convergence of the Laplace transform capital X of S. This is how we should read it. Region of convergence of the Laplace transform capital X as a function of S. So, we do not explicitly need to write as a function of S here. You have just said capital X. And similarly, let us take a sequence and talk about its Z transform as being the output of a Z transformer. It produces capital X of Z with a region of convergence, script r of x again. Of course, here we are talking about two different kinds of regions of convergence. You have seen the kind of region of convergence that a Laplace transform has, and you have seen the kind of regions of convergence that a Z transform has. Now, what linearity really means is these transformers behave linearly. That means, if I were to give alpha times x1 t plus beta times x2 t to the Laplace transformer, the output would be alpha x1 of s plus beta x2 of s, and what is important and somewhat tricky is the region of convergence. What would be the region of convergence of this in general? Well, it is difficult to make a general statement, but what can be said with certainty is that the ROC will definitely include the intersection. It would definitely include the intersection, it could expand beyond the intersection. In fact, let us prove this, a general proof first. In fact, the same thing can be said for the Z transform. Let us first state it and then prove both of them together in parallel, so to speak. So, what we are talking about is the linearity of the Z transform, and that amounts to saying alpha times x1n plus beta times x2n when subjected to Z transformation results in alpha times x1z plus beta times x2z. And once again, what can we say about the region of convergence? All that we can say is that the region of convergence will definitely include the intersection. More than that could be a problem to say. We will now first prove both of these. Consider the Laplace transform of the sum or linear combination. Of course, it is. So, I have alpha x1 t plus beta x2 t, and now let me split, let me use distributivity. Now, this is easy to see. So, in fact, now we can very clearly see that this essentially is capital X1 of S by expression, and the same thing holds for this. This is capital X2 of S by expression. Now, the only issue is to talk about its region of convergence. So, all that we can say, as we can see from this sum here, is that if for a given S, both these integrals converge. Which integrals are we talking about? These two integrals here, this one and this one. If for a particular S, both of these integrals converge, then the sum or that linear combination also converges. And therefore, this S, which is included in the intersection, must also be in the region of convergence of that linear combination. So, this proves what we wanted to prove, that at least the intersection is included, if not more. Now, where does that if not more come from? Let me give you an example, very simple example. Let us take the following sum. We dealt with this in one of the previous sessions. Let x1 of t be e raised to the power 2 tut and x2 of t be e raised to the power 3 tut. We have already calculated their Laplace transforms. We have been doing this, is not it, in the previous sessions. So, the Laplace transform of x1t is 1 by s minus 2 with a region of convergence, real part of s greater than 2. And similarly, the Laplace transform of x2t is 1 by s minus 3 and the region of convergence, real part of s greater than 3. Now, let us take any linear combination. So, for example, let us take 2 times x1t plus 3 times x2t. What would be its Laplace transform? The Laplace transform would of course be, according to this principle that we have derived, 2 by s minus 2 plus 3 by s minus 3, and of course, the ROC is at least the intersection of real part of s greater than 2 and real part of s greater than 3, which is of course the second term, is not it? The intersection is essentially the real part of s greater than 3, and this also happens to be the ROC here. That can be verified. In contrast, if you took the following example, you took x1 of t to be e raised to the power 2 tut plus e raised to the power 3 tut, and you took x2 of t to be e raised to the power 2 tut minus e raised to the power 3 tut, and now you added them. So, you took x1t plus x2t. That would be essentially 2 times e raised to the power 2 tut. Now, the interesting thing is that if you look at their regions of convergence, of course, you can look at their Laplace transforms and the regions of convergence. So, if you looked at the first Laplace transform, it would be x1 of s given by 1 by s minus 2 plus 1 by s minus 3. You can go back and see that. You are summing there and you are taking a difference. So, the first Laplace transform would be 1 by s minus 2 plus 1 by s minus 3, and the second one would be 1 by s minus 2 minus 1 by s minus 3, and both have the regions of convergence given by real part of s greater than 3. Now, when I take their intersection, what do you notice? Their intersection is of course real part of s greater than 3, nothing very great about that. But then if you look at the Laplace transform of the sum is also a linear combination. So, Laplace transform of x1t plus x2t is essentially the Laplace transform of 2 e raised to the power of 2 tut, which is very easily calculated to be 2 by s minus 2, and the region of convergence happens to be real part of s greater than 2, which of course includes real part of s greater than 3, but has expanded beyond. So, it is very interesting. The region of convergence could expand in this process of linear combination beyond the intersection. Now, let me carry you a few steps for the same reasoning in the context of the Z transform. Let me first complete the proof for the Z transform. So, the Z transform of a linear combination is essentially this expression, which can now be broken down, and you can very easily see that this essentially corresponds to capital X1 of Z, and this essentially corresponds to capital X2 of Z. So, this becomes alpha times capital X1 of Z plus beta times capital X2 of Z. Now, again, if a particular Z belongs to the intersection, I am bringing in the symbol for intersection now. You know, this is the symbol for the intersection of two sets or two regions in this case. Then it also allows that linear combination to converge. And so, we have proved that at least the intersection is there in the region of convergence. Now, I am going to leave it to you as an exercise to construct examples similar to what I did in the Laplace transform. The region of convergence could be exactly the intersection, or the region of convergence could expand beyond the intersection. It is not too difficult. Do the exercise, and that will give you some confidence with the Z transform. We will meet again in the next session. Thank you.